Well, greetings, Mr. Kolazar's class. Today we're going to finish out our chapter by talking about the polarity of molecules. So we're going to be looking at the idea of polar, and non-polar molecules. Both are going to be covalently bonded, and then we're going to look at polar and non-polar molecules also, and the idea of still sharing the electrons, but they're just not shared equally. So electronegativity. Remember from last chapter, electronegativity, property or the ability of an atom to attract electrons to itself while bonding. So certain elements want electrons more than others. So whenever a bond forms between different elements, electrons will either be transferred, that'd be ionic, or unequally, this would be covalent as long as they are different elements. So they're still covalent, but they're just not shared completely equally. One atom wants the electrons a little bit more than the other. So electronegativity differences can predict bond character. Nonpolar, polar, or an ionic bonding. In the textbook, page 265 and 266 is where this is at. We will always give you this chart coming up if you need it. So subtracting the differences between the two elements determines what type of bond we have. If that answer, the difference between them, is between 0 and 0.4, it's a non-polar covalent bond. If it's between 0.4 and 0.7, it's going to be what we call a polar covalent bond, where it's still sharing, it's just uneven sharing. Poles, like we've got a plus and a minus side, it's just that there's a little bit more plus on one side and a little bit more minus on the other side. And then greater than 1.7 ionic, where it's a full plus and minus, complete separation of the electron on one atom and not on the other. So this is the chart from page 265 in the textbook, giving us these mathematical numbers describing like fluorines are most electronegative, down to francium and cesium are least electronegative. One electron's least, one electron's the most. Notice group 18 on the periodic table here are noble gases. They don't form compounds, so they don't have electronegativity numbers. So we've already seen this top chart. So nonpolar bonds, math was up above, equal sharing of electrons between the atoms. So they're going to share those electrons equally between the two atoms. A polar covalent bond is unequal sharing. It's still sharing, but it's unequal sharing between the atoms, so it causes a little bit of plus minus. Say the electrons are 40% of the time on one atom and 60% on the other, where it's a little bit different give and take, but not a give and take. A little bit less time over one, a little bit on the other, sharing still. And then ionic is the transfer of electrons, where we have that give-take. No sharing of electrons, it's a full plus minus holding the atoms together, is the difference between those three types of polarity. So if we were to experimentally do this, using that page 265, the difference between the two. So if we had a carbon-iodine bond, if we were to look at that chart, 2.665 and minus 2.55, we get 0.11. On our chart, that would be a non-polar bond. Iodine-iodine, same elements, so same numbers gets us a 0. 0 on that chart would also be nonpolar. Sodium and iodine, 2.66 minus 2.9 or 0.93, give us a 1.7. That would be an ionic bond, where the electron would be around iodine, making that plus minus type bond. And finally, hydrogen and iodine, 2.6 minus 0.2.0 gives us 0.466, which would be a polar bond. Again, remember, all of these numbers are on page 265 in the textbook. You'd be given that chart if we needed. What I need you to remember in your notes, this is number 6, is this is the key one that we actually want to worry about. In practice, what matters most is the molecule is polar, nonpolar, not the bonds. So what you need to know, polar molecules, terminal atoms, those are the ending atoms, are different. Or it has a lone pair or pairs of electrons on the central atom. This means it's asymmetrical. If we're asymmetrical, It's a polar molecule. If the molecule is nonpolar, it's because the terminal atoms are all the same, meaning it's symmetrical. Even if each bond is polar, if overall it's symmetrical, everybody's pulling equally in different directions, it balances out and it makes the molecule nonpolar. So if it's symmetrical, it's nonpolar. So we'll go through a few examples of this. CH4. Every carbon, or the central carbon, 4 hydrogens equally pulling in opposite directions would be our nonpolar because it's symmetrical. NH3 has a lone pair of electrons. That lone pair makes this molecule automatically polar. Lone pair of electrons gives us our polar molecule. H2O. H2O has 2 lone pairs of electrons. If it has lone pairs of electrons around the central molecule, it's going to be polar. A couple more examples. These are from page 4 in your notes. CH2Cl2. If the molecule has different atoms, terminal atoms around the central atom, it's asymmetrical, so it's polar. We've got chlorines over here and hydrogens down here. Different atoms cause it to be polar on one side and nonpolar on the other. O2, symmetrical, so nonpolar. SO2, lone pair of electrons on sulfur, causes it to be polar. And our final ones, ClO4, symmetrical, so it's nonpolar. NH4, symmetrical, even with the plus charge on the outside, all 4 hydrogens equally pulling, so they all balance out. So in the end, both of these nonpolar. And N2O, lone pair of electrons around it, causes it to be polar. So, key part, nonpolar compounds, like dissolves like. We'll hear this in the future. Polar compounds dissolve polar compounds. Nonpolar compounds dissolve nonpolar compounds. An example of this is oil and water don't mix. Oil's a nonpolar and water's a polar compound, and they don't mix with each other because one of them's a nonpolar and one of them's polar. So like dissolves like goes against that, and we see that separation between the two. You can go ahead and finish up the rest of your worksheet number 8 now that you've known the structure, the shape, and now the polarity of those molecules.